All right, we're back. We're on page 2 of notes 2 of Calc CD, Calc C really, because it starts recounting when we get to Calc D. That's like a historical artifact that I will never fix because I have like 1,000 files named that way, and that's you got to think long term when you start naming all your files, people. I'm telling you right now. Like when you name your files, if you're gonna put a date, make sure you go year, so like year, 4 digits. 4-digit year in case you live to, I don't even know, like 2110 or something. You don't want to like 2120, I guess, is where you'd start running into a problem. Year and then month, 2 digits, so like 0, 1, not just 1, and then day. Also use 0, 1, and that when you sort your files. This is neither here nor there really, but when you sort your files later in life, oh, it'll be so much easier. So anyway, not related. What is related is that we are now going to talk about how do you go in the other direction, right? So on the last page, we were given a function, we were given its Taylor polynomial to a certain degree. And then what we did was we just confirmed that the values of the, let's just look, the values of the derivative were equal up till whatever degree polynomial you had. So second degree polynomial, second derivatives should be equal, and the first and the original function. And then also we compared some values, right? What we're going to try to answer on the next page, where do these polynomials come from? So we're going to do it. It's like, you know how to do this, but it feels weird at first. So what we're going to do, we're just going to construct a polynomial with a given information, right? So we're going to construct a 5th degree it's not really a Taylor polynomial unless it's like for another function, but we're going to construct a 5th degree polynomial that satisfies the information in the table. So what we're going to do is we just assume that the last derivative that we're given is a constant. So the 5th derivative at 0 is also the 5th derivative everywhere in this case. So the 5th derivative everywhere is 13. So we can go from that and get the 4th derivative, the same way that you would go from the first derivative to the original function, right? Like integrate. So what we're going to be able to do, though, is a definite integral. So we know that the lower bound, because the center, right? The center is where all the derivatives were evaluated, is 0. So we're going to make the center the lower bound, and then we'll make the upper bound be x, so that we end up with a function of x for our 4th derivative. So let's see if we can do that. So this, if I integrate it, is going to give me c plus. So here's how it works. It's 13t, but we're going from 0 to x, which means it's, we're going to have c plus 13, the quantity, x minus 0. And that's it. So we get this quantity x minus 0. You don't need to write that. You could just write x. But it's a good idea to start here. And now I need to solve for c. So how am I going to do that? Well, I know that the 4th derivative at 0 is 11. So since I know that p4 of 0 is 11, I automatically know that c here must be 11. Because if I plug in 0 for x, and then set, you know, because you know that. All right, so let's see if we can then take that information and find p3. So p3 of x is going to be a new c, we don't know what, plus the definite integral from 0, which is the center, to x, which is the variable we want to end up with, of p4, right? If I integrate the 4th derivative, I should get the 3rd derivative. And the 4th derivative worked out to 11 plus 13, the quantity. We have to use a dummy variable, so not x. I'm going to use t. I'm going to write t minus 0, I guess. No, I'll just write t. I don't know. I'm going to write just t. And then, whoops, dt. Close your parentheses. All right. So here, we're going to notice the c is outside of the integral, which it should be, because that makes sense. So it's c plus, if I integrate 11, I'm going to get 11t from 0 to x. So I'm going to write 11 quantity x minus 0 plus 13 over 2, the quantity. So I get t, but from 0 to x, so the quantity x minus 0, but then squared. All right, so we have this so far. Now, I know from the table that the third derivative at 0, because everything is at 0 in this table, third derivative at 0 is 7. So I know that P3 of 0 equals 7, which means that C, when I plug in 0 for x, everything else goes away, must be 7. All right, let's find the second derivative. So P2 of x is going to be C plus the integral from 0 to x of the quantity 7 plus 11 t plus 13 over 2, sorry, 13 over 2, 13 over 2 t squared, and then dt. Okay, so when we integrate this, we're going to get c plus 7. We'll end up with x minus 0. So usually like you integrate and evaluate like in the same step because it's a very common process. 11 halves x minus 0 squared plus, now a weird thing is happening. I'm going to get 13 over 2 times 3. So I'm gonna write it that way, which is a weird way to write it, admittedly. And then x minus 0 cubed. Now we need to be able to solve for c, but again, we know that the second derivative at 0 is 5. So P2, or P double prime, I guess. I'm gonna write P2. P2 of 0 is 5, which lets us say that for sure, this value of c is definitely 5. So really, we can find P prime, which I'm going to write P prime, I think. So P prime is c plus 0 to x of, what was it, 5? Yeah, 5. So we're always using the antiderivative that we found. 5 plus 7t plus 11 over 2 t squared plus 13 over 2 times 3 t cubed dt, which, all right, I'm gonna have trouble fitting this on the line, but so I'm gonna jump down here. So that's c plus, we'll get 5, the quantity x minus 0 to the first, plus 7 over 2, the quantity x minus 0 squared, plus 11 over 2 times 3, x minus 0 squared, cubed, squared, get out, plus, so what's happening here, right, in these denominators? 2 times 3 times 4, x minus 0 to the 4th. So these, if you look at these denominators and you recognize them, which maybe you do, got 2 times 3 times 4, 2 times 3, 2 times 1, this is 1 here. These are actually factorials. Not only are they factorials, they're factorials that match. So this matches this. This is 3 factorial. Here, it matches 3. This is 4 factorial. It matches 4. I bet we could guess what the next antiderivative is. I bet they're all just going to be, I bet you're going to get a 13 over 5 factorial, x minus 0 to the 5th, and so on. And so this is what we need to do. We need to work out the pattern. So here, what was P prime? P prime of 0 is 3, we can see. So because of that, so P prime of 0 is 3. So, I mean, I guess because I've been highlighting, that means that this C value, when you plug in 0 for x, you just get C is 3. I think we can do a pattern type thing here. So I'm going to say that P of x is just going to end up. So what is the value at 0? It's 2. I think we're going to get 2 plus, 5, what was C? C was 3. So this is where I'm killing myself. You know what I should do it the long way? All right. I might move this up though. Here we go, long way, because I don't want to. I want to generalize. The problem is I already know the answer, you know. So like generalizing here for me feels simple, That does not mean it feels simple for you, nor should you feel bad if right now you're like, what is happening? Because there's a lot happening, right? So we get 5t, 7 halves t squared. So basically what I'm doing is like just kind of integrating each of these as I go. I am going to use factorials here though. So this is going to be plus 11 over 3 factorial t cubed plus 13 over 4 factorial t to the 4th, and then dt. All right, we're going to integrate, we're going to solve for c, and when we do that, we're going to get, so c plus, this is going to give me 3x plus 5 over 2 factorial x squared plus 7 over 3 factorial x cubed plus 11 over 4 factorial x to the 4th. I'm doing something right now that I realize I did not explain. 5 factorial x to the 5th. So let me just explain really quickly that, you know, if you do n factorial time, no, what are we doing? N time, if you do 3 factorial times 4, that's just 4 factorial. So I guess if you do n factorial, here we go, n factorial times n plus 1, you will get the quantity n plus 1 factorial. I'm like taking for granted that we know that, which it's definitely not something to be taken for granted. All right, and then finally, the value of the 0th derivative or the function at 0 is 2, which means down here c is 2. So p of x is going to be 2 plus 3x. So that's really like 3x to the 1st over 1 factorial, which, you know, you could write that way, but I don't think you want to. Although you'll find that I do that all the time. X squared plus 7 over 3 factorial x cubed. So the factorials seem to match the exponent of like x minus the center. And then let's take a look at the coefficients, right? So the numerators basically. So we have like 13 is over 5 factorial x to the 5th. Go to the table. 13 is the 5th derivative. So we have the 5th derivative, 5 factorial, 5 is our exponent. So here we have 4 is our exponent, 4 factorial is 11 the 4th derivative. 11 is the 4th derivative. So the next one should be, because this is 3, it should be 7 over 3 factorial and then times x cubed. 7 over 3 factorial times x cubed, which we got. That's the pattern. That pattern just showed up on its own. We didn't really need to do anything to make the pattern. We just need to keep integrating. And that's what we're going to use. We're going to take advantage of that pattern so that we don't have to go through the process. That's our plan, is to not go through this process. So maybe back in the next video, I think I'll do the process one more time. It's like a really long process though, so I'm not like super stoked about that, but it's okay because sometimes you just got to put in the hard work so that like later on it feels like the easy work, I guess. I don't know. Anyway, I'll see you in the next video where we will hopefully finish this page. So see you there.